Unlike the previous problem, this is a multi-step problem because the same sample is going through a phase change, or it's going through multiple phase changes. We have a sample that is 152 grams at ice, negative 37 degrees Celsius, and it becomes liquid water at 0 degrees Celsius. To determine the number of equations to use, it is easiest if you draw or sketch out the heating cooling curve. Since we know the substance is water, water freezes or melts at 0 degrees Celsius. It boils at 100 degrees Celsius. The water starts at negative 37, which is below 0 degrees down here. It goes to 0 degrees Celsius liquid water, which is at the end of its melting point. The end of the melting point is at the right side of the first plateau, 0 degrees Celsius. Every single time there is a slope change, you must use a different equation. Each slope represents a different constant. So for this problem, there are two slopes. We have a slope from negative 37 to 0, and then we have 0. So if we start at negative 37, there is a change in temperature. So my Q is going to equal to mc delta T. At the melting point, there is no change in temperature, so we're going to use mHF, which is mass times the latent heat of fusion. So here we know that the mass is 152 grams. Since the substance is at solid ice, we use the C of ice, or C of the solid ice, which is 2.03 joules per gram degrees Celsius. We also need HF. HF is also a constant, which is 333 joules per gram. If you notice, these numbers are slightly different from the table that I provided in class. Will also be different from the table that is in your textbook. All the constants will be given to you unless you have to solve for it. Now we're going to plug in. So the mass is 152 grams. C, solid ice here, is 2.03 joules per gram degrees Celsius. Temperature change. Remember, triangle means final minus initial. The initial temperature, we started at negative 37 degrees Celsius, and solid ended it at 0, so T final has to equal to 0 degrees Celsius. So this is going to be 0 degrees Celsius minus a minus 37. A minus and a minus becomes a plus. Plus MHF, the mass of the ice is still the same, 152. Heat of fusion is 333 joules per gram. So we're going to first multiply MC delta T and get 11,416.72. And then MHF, which is 50,616. So now we do sig figs. So the 0 that is given in the problem does not count because we just picked that number. The mass has 3 sig figs. This is a constant we ignore, and the temperature has 2 sig figs. So for Q equals MC delta T, there is 2. So we start on the left, go to the first non-zero digit and count 2. 1, 2. Look 1 to the right. It is less than 5, so it stays. So that's 11,000. Q equals MHF. There's 3 from the mass. This is a constant, so my final answer is going to have 3. So I start at the left at the first non-zero digit, which is a 5. 1, 2, 3. I look 1 to the right, and this is also less than 5, so the 6 stays. So it becomes 50,600. So now I need to add. So if I add these two numbers, the least precise position is at the 1,000. So this becomes 61600. I look 1 to the right. So this becomes a 2. And we need to add 3 zeros for a placeholder. The better way to write this is 6.2 times 10 to the 4th joules. Pause the video, solve the problem, and then check your answer. This problem 2 is a multi-step problem because it is starting at steam, which is 121 degrees, and it is cooled to ice at -14. So it went from a gas to a liquid to a solid. To help you out again, you want to sketch out the heating cooling curve of water. We know down here it's going to be 0 degrees Celsius where water melts and boils. Up here it's 100 degrees Celsius where water boils. It's starting at 121 degrees Celsius, which is way up here, and it's going all the way down to -14, which is way down here. So every single time there's a slope change, it means that there is a new or different constant. That means we must use a new equation. So we're going to start with 121. The sample can only stay as a gas until it reaches 100 degrees. So my first equation is going to be Q for my steam is going to equal to mc delta T because there's a change in temperature. At this point right here, we are at 100 degrees steam. Since we are at the horizontal or plateau, we need to condense it. When we condense, there is no change in temperature. All that energy or potential energy, heat energy that is being removed is to make the intermolecular forces stronger. So the equation I will use here is Q is equal to mHV, which is the latent heat of vaporization. After we condense it, we are at 100 degrees water, and we're going to cool the water down to 0. Liquid water only exists between 0 degrees Celsius and 100 degrees Celsius. Since there is a temperature change, Q for the liquid is going to be mc delta T. When we reach 0 degrees Celsius, this is 0 degrees water. Again, we're going to undergo a phase change. This is when we are removing the heat or the potential energy to make the intermolecular forces even stronger. So here we're going to freeze, and since there is no temperature change, Q is equal to mHF. Here we're at 0 degrees ice, but we want to go to -14 degrees Celsius. So we're going to go all the way down here, making the solid ice even more solid because we're removing more heat and potential energy. At this point, there's a temperature change. So Q solid or ice is going to be mc delta T. So now I'm going to identify the variables. We know that mass is equal to 218. We know that the initial temperature is going to be 121 degrees Celsius. And we are going to go to the final temperature of -14. But this is not exactly the final temperature when we break down the problem. C of the steam is 2.06 joules per gram degrees Celsius. The HV is 2260 joules per gram. C of the liquid is 4.184 joules per gram degrees Celsius. Heat of fusion or latent heat of fusion is 333 joules per gram. And then C of solid or ice is equal to 2.03 joules per gram degrees Celsius. These values are slightly different from the table that I provided, but it varies from table to table. But the process to solve these problems are the same. Now that I identify all the variables, plugging in the numbers. So Q steam, we're going to have mc delta T. Mass here is 218 grams. The C for the steam is 2.06 joules per gram degrees Celsius. Equation is T final, right here, change in temperature, minus T initial. The final temperature is 100 degrees Celsius, not negative 14. The reason it is 100 degrees Celsius, right here, this is steam or gas. Once it goes below 100 degrees Celsius, it's no longer steam. So you cannot use the steam or gas constant. My initial temperature was 121 degrees Celsius. Our first Q equals MC delta T brings us right here at this point. Now I need to condense it. When I condense it, I'm going to use MHV. The mass again did not change, so it's 218 grams. The heat of vaporization is 2260 joules per gram. After we condense it, we are at 100 degrees water. So now we are completely liquid. QL is the energy of the liquid. The mass is still the same. Liquid, we're going to use 4.184 joules per gram degrees Celsius. Delta T again is T final minus T initial. My final temperature is 0 degrees Celsius and not negative 14. Water only exists in liquid state between 0 and 100. So to use the constant for water at liquid, we need to only be between 0 and 100. So my final is 0 degrees Celsius. My initial is 100 degrees Celsius. At that point, we are here at 0 degrees liquid. We need to freeze it. So we're going to use MHF. Mass is still 218 grams. Latent heat of fusion is 333 joules per gram. Now we're at 0 ice. We're going to even make it a stronger ice by lowering the temperature. Here it's going to be QS is equal to MC delta T. Mass is still the same. Our constant for ice is 2.03 joules per gram degrees Celsius. Our final temperature here is negative 14, but our initial temperature is 0. This is where ice actually starts. Now plug into the calculator. The steam equals to negative 9,430.68. Condensation equals to 480,908. The cooling of the liquid is negative 91,211.2. The freezing is 72,594. And making it a harder ice is 6,195.59 negative. Quickly going back and doing sig figs, there's 3 here. Constant doesn't count. We wrote this as 100, so it doesn't count. So there's 3. My final answer has 3. I start from the left. The first non-zero digit is 9. So 1, 2, 3. I look 1 to the right. The 3 stays. So this becomes negative 9,430. The next one, this is 3. Constant does not count, so I need 3 in my answer. 1, 2, 3. I look 1 to the right. Since it's greater than 5, the 0 becomes a 1. So this is 4, 8, 1, 0, 0, 0. We need the zeros for placeholders. In the next one, there's 3 from the mass. The constant doesn't count. These will not count because we picked it, so it's 3. So starting from the left, first non-zero digit is 9. So this is 1, 2, 3. I look 1 to the right. It's less than 5, so the 2 stays. So this becomes negative 9, 1, 2, 0, 0 for placeholders. In the next one, there's 3. This doesn't count, so my final answer has 3. 1, 2, 3. I look 1 to the right. It's greater than 5, so the 5 becomes a 6. That's 7, 2, 6, 0, 0. Mass has 3. Constant doesn't count. There's 2 because we picked this number. So my final answer has 2. So it's 1, 2. I look 1 to the right, greater than 5. So the 1 becomes a 2. I'm going to rewrite the numbers down here so it's a little bit clearer. So the Q steam, when we did sig fix, was 9,430. Q of the condensation equal to 481,000. Q of the liquid was equal to negative 91,200. Q of the heat of fusion, or freezing here, was equal to 72,600. And then Q of the solid ice was equal to negative 6,200. So if you look at my Q's, half of them have a negative sign and the other half are positive. Since the problem said it went from steam, if I resketch the heating curve, it went from steam and it went down to ice. So that means heat is being removed. When heat is being removed, it is an exothermic reaction. Exothermic reactions are negative in sign. When you use MC delta T and you write the final temperature minus initial temperature correctly, the correct sign will come out. However, when you have MHV and MHF, Q will always be positive because mass is always positive and the two constants are always positive. So when you are going through an exothermic process, you must as negative. So instead of adding and subtracting here, we're going to add all of these and it's going to be a negative value. So if I add all of these values together, 660,430. The least precise position for the first one is the 3. For the condensation is the 1. For the liquid is the 2. For the freezing it's the 6. And for the solid it is the 2. So the least precise position is going to be the thousandths. So I'm going to round it right here. So I look 1 to the right, it stays because it's less than 5. So this is going to be 6.60 times 10 to the 5 units of joules. And if you notice, they all have a negative sign. Exothermic reaction, it's a minus. Pause the video, try this problem on your own, and then check your answer. This problem is also a multi-step problem because it's water going through multiple phase changes. It's starting at 21 degrees Celsius and it's becoming steam at 140 degrees Celsius. Sketch out the heating cooling curve. Mark where it starts, which is 21 degrees here because we know the first plateau is 0 degrees Celsius, the melting freezing. Up here is 100 degrees Celsius, which is boiling. And it's going to go to 143, which is up here. So there are 3 slopes. That means there's 3 constants. So there are 3 equations. So we're starting down here, which is the liquid state. So the first part is going to be liquid, which is MC delta T of liquid water. Then we are going to vaporize at the boiling point. That's going to be Q is equal to MHV, the latent heat of vaporization. And then from there, from steam, we're going to make it even hotter steam. So that's going to be Q steam is going to be MC delta T. So if I identify the variables, mass is 79 grams. My initial temperature is 21 degrees Celsius. We are going to go to a final temperature of 143 degrees Celsius, but this will not be true for all the parts of the equation. Since we are studying at liquid water, we know C of liquid is 4.184 joules per gram degrees Celsius. We know the heat of vaporization is 2,260 joules per gram. And we know that C of the steam is going to be 2.06 joules per gram degrees Celsius. So now we're going to plug it in. So the mass is 79 grams. The C of the water is 4.184 joules per gram degrees Celsius. Delta T again is T final minus T initial. So the final temperature is not 143. It is only a liquid up to 100 degrees Celsius. So T final is going to be 100 degrees Celsius minus the initial temperature, which was 21 degrees Celsius. At 100 degrees water, now we need to vaporize it. We're going to boil this. So we're going through a phase change. The mass is still the same, and the heat of vaporization is 2,260 joules per gram. After we vaporize, we are at 100 degrees steam. We're going to make the gas even hotter using MC delta T. The mass is still 79 grams. C of the steam is 2.06 joules per gram degrees Celsius. Our final temperature we're going to reach as steam is 143 degrees Celsius minus, remember, steam starts at 100 degrees, so our initial temperature has to be 100 degrees Celsius. So if we multiply the liquid, it becomes 26,112. The vaporization is 178,540. And then the steam is 6,794. Now I'm going to quickly go and do sig figs. There's 2 for the mass here. This is a constant, doesn't count. We picked this number, so it doesn't count, so there's 2. My answer is going to have 2. 1, 2. I look 1 to the right. This 6 stays. This is 26,000. I need the zeros for placeholder. There's 2 here. These are constant, does not count, so I'm going to have 2. 1, 2. I look 1 to the right. So the 7 will become an 8. So this is 1, 8. Everything else has to be 0. So I need to add 4 zeros as placeholders. The last one, I have 2 sig figs here. That's a constant. We picked this number, doesn't count. There's 3. My final answer is going to have 2. 1, 2. I look 1 to the right. It is greater than 5. So the 7 becomes an 8. So now I'm going to rewrite the numbers below here. So we can look at it a little bit closer. So Q of the liquid with sig figs was 26,000. Q of the vaporization was equal to 180,000. Q of the steam was equal to 6800. If you notice, these will all be positive because we are increasing the temperature. So this is an endothermic process, as I stated in the previous problem. So you could double check if your sign is correct, because if you do the T final minus T initial correctly, the correct sign will come out. Here it came out positive, and we know it's an endothermic process. Why? The temperature increased. So it has to absorb energy to become a gas. This also will tell you that Q of the vaporization or heat of fusion will be positive or negative. Since this is endothermic, the Q of the vaporization here is right sign. It is positive. Now we're going to add all of these numbers together. Last significant digit is the 6 for that one. For the vaporization is the 8. For the steam is the 8. So the least precise position is right here. So I'm going to round here, 1 place to the right. If you notice, it's a 2 less than 5. So the 1 stays. I'm going to put this in scientific notation. 2.1 times 10 to the 5th units joule. And if you notice, it should be positive because it's an endothermic process. You will have multi-step problems, meaning there is going to be more than 2 equations. If the same substance goes through multiple phase changes. To determine the number of equations, sketch out the heating cooling curve. Mark where you start, mark where you end. Each time there's a slope change means the constant is changing, so you must write a new equation. In addition, anything that is endothermic will all be positive. Anything that is exothermic will all be negative. If you do T final minus T initial correctly, the sign will come out. For Q equals MHV and Q equals MHF, you need to keep track of the sign. If it's exothermic, then you need to stick a negative in front. Q equals MHF and V will always come out positive because mass and the constants are always positive. In addition, make sure you note the temperature when it goes through a phase change. For example, for water is only a solid below 0 degrees Celsius. So you can only use C of the solid when it's below 0. You can only use C for the liquid water when it's between 0 and 100. And you could only use steam constant for C when it's above 100. You cannot go from 143 to negative 14 with one constant.